In our first section of this lecture, we talked a little bit about Newton's laws. And as a part of that discussion, I said that these three laws of motion that Newton came up with 300 and change years ago now were truly a stroke of genius. He was looking at the world in a completely different way than everybody else. And of his many contributions to physics, laws of motion, universal law of gravitation, studies of light, on and on and on, this is one of those huge parts that were really counterintuitive to what people saw in the day. Now, why do I bring this up? In our last part of the lecture, in part B, we were looking at these free body diagrams where we could take some object, we could see how forces were interacting with that object. We sum up what all those forces are to find a net force, and that tells us what the acceleration of that object is going to be. And the kinds of forces that we looked at were tensions, or maybe pushing on an object, or maybe the weight of an object, normal forces. These are the kind of forces that we dealt with, but one of the major exceptions was friction. And what I just brought up at the beginning of this video and relating it to what we saw in the last video, man, friction is a little bit weird. So let's take ourselves back 300 and change years ago. Newton is looking out his window and seeing how things progress. And maybe he sees some worker in a field pushing a cart. Now, the question to you is, if that worker stopped pushing the cart, what happens to the cart? And hopefully that you would say, I think the cart would stop. It might roll for a little bit, but eventually it would stop. He stopped pushing on it, and so the cart is going to stop. That's what people see. That's what people experienced. Is that completely true? What if instead Newton was by the side of some lake and saw somebody get into a boat and somebody pushed the boat off? Now all of a sudden this is another situation where the person stops pushing and we want to observe what happens. And the boat is going to go further than the cart, almost certainly. But eventually even that boat is probably going to stop. It's not going to make it all the way across the lake. It'll go for a long distance, but not all the way. We could even continue on to maybe an ice skater, or somebody that's on a sled or something, gets pushed on an icy surface of some kind, and it goes further still, but still will eventually stop. When you look as a non-physicist at some progression of these events, what I see is if I stop pushing it, it will eventually stop moving. And Newton saw something different. He said that this condition of me stopping pushing it is not the regular thing. I'm not able to account for all of the forces. And if I was able to account for all of the forces, it wouldn't stop. It would keep its state of motion. And he got inspiration by studying the planets, seeing how the moon revolves around the Earth and doesn't seem to speed up or slow down. So there were things that inspired it, but it was really counterintuitive to what he really experienced in life and what his contemporaries experienced in their life. This was the stroke of genius. Not pushing an object and having it continue on as though nothing had happened. That's different than our everyday experience, but that's the real nature of things. And so through this discovery, we learn to work with friction. Obviously, if we are able to minimize or limit the effects of friction in our system is going to progress much more naturally with our intuitive nature in Newton's laws. So his first law says, hey, if you don't put any forces on some object, it's going to keep doing what it was. And that's true if there's no friction in the case of that worker in the cart. And we get some assurance that this is going to be the case because the boat is able to go further than the cart. And the sled is able to go further than the boat. So in these situations where I can limit those effects of friction, it does tend to do something like that. Eventually those things do stop, because there is friction and we can't completely eliminate it, but the moon is still revolving around the Earth and has been for eons. Planets have been going around the sun for eons, seemingly unimpeded by any kind of friction. So if we can eliminate or minimize the effects of friction, we're going to see the effects of Newton's laws much more naturally. So in this video, I want to spend a little bit more time talking about these effects of friction and how they're going to change some of our problems. We've already spent some time looking at free body diagrams, figuring out how to apply these different forces. But here, we're going to add one more force to the problem to see what's going to come out and how we can analyze and study the effects of this frictional force. So to get started, let's go here to OneNote. And we're going to look at friction a little bit. There are two things that are going to contribute to friction. One of these things, the amount of friction that we're going to have, a frictional force we're going to have in our problem, is proportional to the normal force. So this frictional force, it happens between surfaces that are rubbing against each other, or ideally not rubbing, if you wanted the friction to actually have that sort of a scenario. But there's some relative motion between two surfaces to get it. And because some object, say, is in contact with another object, there is a normal force. There's a normal force of object 1 on object 2. There's a normal force of object 2 on object 1. So there's a normal force that's there, a force of relativity, but a relational force, this contact force between two different surfaces. And that is a normal force. But it's also proportional to this thing. It's a dimensionless quantity called the coefficient of friction. It's dimensionless because frictional forces have to have units of forces, and normal force is already coded into it. So if a normal force has units of force, and we want frictional forces to have units of force, we can't have anything that's different. But this unitless coefficient of friction is obviously going to be different for different kinds of surfaces. Rubber on rubber seems to have a different feel to it than steel on steel, or wood on wood, or skin on skin. These are all different kinds of relationships between surfaces. And so that's what leads to these different coefficients of friction. And not only that, depending on what surfaces that we're dealing with, there may start with some relative motion between them, some sliding, so to speak. But sometimes we don't have sliding, and we want to minimize sliding. And these are two different scenarios. If there is no relative motion between the surfaces, we are said to use a static coefficient of friction. But if there is relative motion between surfaces, that's when we have a kinetic coefficient of friction. What's the difference? Well, first off, the static coefficient of friction is typically larger than the kinetic coefficient of friction. How do we know this? Well, I would say this. Have you ever helped your friend try to move a sleeper sofa or something very heavy? What you might find is it takes a lot of exertion for you to get that sleeper sofa moving. But once it's moving, you want to keep it sliding, because I don't have to exert myself as much to keep it sliding. It took a lot of effort for me to get it started. This is what's telling me that the coefficient of static friction is bigger than the coefficient of kinetic friction. Once it's sliding, it's easier to keep pushing. That's here, because the normal force on that couch never changed. The only thing that can change is the coefficient of friction, and that's why once it's sliding, it's easier to keep it sliding. Now, we often think that friction is going to impede motion, and on a free body diagram, it is going to oppose some relative motion between these two surfaces. So friction will be in a direction that will keep the object from moving if it isn't moving, and friction will be in the direction opposite to velocity if it is moving. So acceleration and velocity are different, and so our frictional force is not determined by what happens with acceleration in some Newton problem. It's determined by what happens with velocity. And while I say that friction can impede motion, there are lots of scenarios where friction is necessary in order to get motion. In fact, we can use friction to accelerate an object, accelerate in a positive way, make it go at a faster speed. So one of those things is, say, me. And when I'm walking around, I don't want to be sliding, right? I want to have some positive friction between my foot and the ground. Because if there is positive contact between my foot and the ground, and there isn't any sliding that's involved, Newton's third law says that me pushing off the ground with my foot means that the ground is pushing off of my foot in the exact same way. By me pushing back with my foot onto the ground pushes me forward and allows me to walk. That's Newton's third law. But it wouldn't work if there was no friction. Friction is needed to get motion in that sort of a scenario. Or let's say we were to go back to Newton, and he's studying the moons and he's studying the planets. And here in a more contemporary world, we might be looking at satellites. And if our satellite gets too close to the Earth's atmosphere, frictional forces of this interaction of the satellite with the atmosphere, first of all, will start to make that satellite glow and get hot. But it's a frictional force that we intuitively think, well, isn't this going to slow the satellite down? And we're going to find out when we do our discussion of satellites and universal gravitation that that's part of the problem. So yeah, there is a frictional force that's speeding down, slowing down some translational motion. But by taking energy out of the problem, the satellite starts to move down, and there's going to be conservation of this thing called angular momentum. And so even though there is this influence that could be slowing the satellite down, as it descends into the atmosphere, it actually speeds up for a while first. Frictional interaction with the atmosphere speeds up the satellite before it slows it down and gets into more thick and viscous and dense atmospheres. So friction really can speed things up, just like slowing things down. But in all of those scenarios, particularly the ones of interactions between two surfaces, what friction is trying to do is minimize the slide. It's trying to minimize this relative motion between two surfaces. Now, in a free body diagram, we don't typically look at velocities right away. We typically look at accelerations and we look at forces. So the reason why I say that these frictional forces, once we know what they are, have to be opposite to the direction of velocity is just to remind you, velocity is not coded into the free body diagrams. We look at a lot of different vectors on the free body diagrams, but velocity is not one of them very often. So just be careful about the direction that you put the frictional force on your free body diagram. What happens if I guess wrong? Well, it turns out that if you guess wrong and you do your whole problem, you'll start to get things that are a little unphysical. You might get accelerations that were negative, or forces that were negative, for example. And you think to yourself, didn't that just happen in the last video? It was possible with the Atwood's machine where M1 could be bigger than M2 and M2 could be bigger than M1. And all we said is it's going to change the sign of acceleration, so one falls instead of the other. What's the big deal? Nothing changed in those free body diagrams because of our guess of direction of acceleration. However, if we guess the direction of frictional force incorrectly, our free body diagram is wrong. The arrows aren't pointing the right direction. We have to rewrite our free body diagram to get physical results then. A minus sign in a problem with friction can, it's not always, but it can be very problematic because it implies that we probably drew our free body diagram wrong. So often with these frictional problems, we want to be very, very careful to make sure that we get answers where we know what the sign is so that we can determine if we got a negative sign, we might have to go back and reassess things. But we also want to make sure, just as the influence of this, how do we go about creating a frictional force that is going to minimize relative motion between two surfaces? Now, this relationship between the normal force and the frictional force, both of these things are vectors. They're both forces. And we're multiplying this normal force times some coefficient of friction to get some other force vector. But this dimensionless coefficient of friction, it's just a number, right? So I want to also caution that frictional force is equal to mu, coefficient of friction, times the normal force. That's not a vector equation. because the frictional force vector is not in the same direction as the normal force vector. This is not a vector equation. It's a magnitude equation. Frictional forces have to be parallel to the surface. Normal forces are perpendicular to a surface. Okay. One last thing to note. There's these two scenarios, coefficient of static friction, coefficient of kinetic friction. Static friction when there is no relative motion between surfaces. Kinetic friction when there is relative motion between two surfaces. If we have that relative motion between surfaces, we explicitly know what the force of friction is going to be. It will be the dimensionless coefficient of kinetic friction times the normal force. This is an equal sign. That is the magnitude of that force. However, if there is no relative motion between two surfaces, the frictional force can be anything smaller than the coefficient of static friction times the normal force. So it is possible the frictional force could be zero in that scenario. And how do we know that? Well, I can go back to my coffee cup sitting on a book, right? And the question is there a frictional force on the coffee cup? And it's casual to think that, yeah, there probably is. In fact, as I move the cup around, you can hear it sliding on the surface of the book. Except for the fact that if there was a frictional force on this cup, it would be unbalanced with anything else in the problem. A frictional force on this cup is a force in the free body diagram that would have the cup taking off of this book and crashing on the floor, which I don't want to happen. In this scenario, there is no frictional force on this cup, even though we have two surfaces with a coefficient of friction between them, even though there is a normal force being applied to this cup. Just because we have a possible coefficient of friction, just because we have a possible normal force, does not mean that we have frictional forces. Now, if I start to angle the book a little bit, now there is a frictional force on this cup. If there wasn't a frictional force on this cup, the component of weight down the slope, and it has to be balanced by the frictional force up, because I don't see the cup accelerating. Cup's not accelerating. So there must be a frictional force being applied. Eventually I'll get to a steep enough angle where the cup will start to slide. That's when we get to the equality of this scenario and not the inequality. The frictional force being less than the static coefficient of friction times the normal force. So these are some things to kind of keep in mind. Now, that being said, how does this show up in some free body diagram? And we might want to start with essentially the way we started in the past. So let's go here to just a piece of paper. What if we were to have some plane and we have some block that's sitting on the plane, mass m. And as we did in the previous video, we apply some force at some angle theta with respect to the normal. First of all, what are we going to do constructing a free body diagram? There's a couple of forces that are at play. One of them we've already handled right here. But what other forces are at play? We've already seen cases where there's a normal force. So we know about that one. In the last video, we knew about this weight force, mg. But if I start tugging on this block, what we found is that there was an acceleration this way. If we wait until the instant where it starts to move, velocity throughout the problem is going to be going that way as well. And that's what tells me that there's an additional force here, a frictional force of magnitude coefficient of friction times n. And we're going to look at the case of sliding, so we'll call it mu k if we want. So this is the setup that we have. Now I haven't added any numbers yet, haven't added what we're looking for, but some things that we already know about this problem are what happens along the horizontal and the vertical. Let's do the horizontal first. If I look at forces to the right and to the left, I see that F cosine theta is to the right. I see that mu sub k times the normal force is to the left. This has to be equal to mass times acceleration. I also see a normal force up. I see F sine of theta up. I see mg down, but my acceleration is not up or down. So this has to be equal to 0. So in this equation, I know the force, I know the angle, I know the mass, I know g. From this, I could find the normal force. Once I know this normal force, I could plug in over here, and I could find something else. So depending upon what kind of problem that I have, maybe I wanted to find the acceleration. In this two sets of equations, I have two unknowns, normal force and acceleration. So I can solve this uniquely. So first of all, I see that the normal force is going to be mg minus F sine theta, just like it was before. Because this person is pulling up at some angle, I am lowering the normal force. But once I know this normal force, I can plug that in to this equation, where we find that F cosine of theta minus mu sub k mg minus F sine theta is going to be equal to m times a. So from this, I could find out what the acceleration is going to be. Rearranging terms a little bit, we see that the acceleration in this problem is going to be F cosine of theta minus mu k mg minus F sine theta over m. So I can find numbers for normal forces. I could find numbers for accelerations if I wanted to. But before we go there, I just want to casually look at a couple of different scenarios. So I had this person pulling with some string, lowering the normal force. Because this person is pulling with the string, we've got a minus influence that shows up here with a minus sign with the coefficient of friction. So it turns out because he is pulling on it and lowering the normal force, he is also lowering the coefficient of friction, and so at some bigger angle theta, we're getting bigger accelerations. As this angle gets smaller, the sine of this angle gets smaller as well, and we're having a larger normal force leading to lower accelerations because of this minus sign. So there's a lot of math coded into an expression like this telling us that the coefficient of friction is going to lower our accelerations. That's what this minus sign does. But if I have some person that's pulling with this force F at a large enough angle, the normal force gets smaller and the acceleration can go up even though there is a coefficient of friction. Notice here, if the coefficient of friction mu sub k goes to 0, we get exactly the same answer that we got when we didn't have friction before. Setting the coefficient of friction equal to 0 is the same thing as saying that there is no friction. It doesn't alter the normal force, whether there is a mu or there's no mu. The normal force is the normal force. But if we were to alter or change the normal force, that's going to change our accelerations because it changes our frictional forces. So this is one of those scenarios that we can kind of look at. But the next thing I want to study is the case of some inclined plane. We do a lot of stuff with inclined planes, and we did in the last video as well. Okay, so let's say we have a block on an inclined plane, and we want to look at some of the forces on this block. As always, there is a normal force perpendicular to the surface, there is a weight, mg down. But if we were to let go and this just started to move, maybe we want to look at some scenario where it's not moving yet. Let's actually look at the case where acceleration and velocity are both equal to 0. The block is sitting there, but it is on an inclined plane of some unknown angle. I'll call it theta here. Could we come up with some scenario where the acceleration and velocity are both equal to 0, and the block just sits there like the coffee cup did on the book at some angle? The only way that's going to work is if the sum of the forces goes to 0. And here I see that, yeah, I could probably code some way to get this perpendicular component of force to 0. I don't have any way to counteract this component of weight that's down the plane, unless I have friction. So frictional force must be this way. Okay. So let's say we have this scenario. What are some equations that we have? We remember that this angle is going to be theta. This is a right triangle. So perpendicular to the plane, I see that n minus mg cosine theta is equal to ma in this perpendicular direction. But that's equal to 0. Up and down the plane, I see that we have mg sine theta down the plane, but I have mu n up the plane. Those are all the forces up and down. There's no acceleration. This is equal to 0 as well. So from this set of equations, if we were to know what's going on in this, could we find the angle where this starts to slide? Starts to slide implies that this is a coefficient of static friction. So now looking at this, I see over here that the normal force is mg cosine of theta, something that we've seen before. I can plug that in over here to find that mg sine theta minus mu s normal force is mg cosine theta. This is going to be equal to 0. Interesting. Okay. So mg sine theta is equal to mu s mg cosine of theta. M doesn't seem to matter. M doesn't seem to matter. G, those don't seem to matter. What I see is that if I divide both sides by cosine theta, this becomes tan theta, and what's left over here is mu sub s. So if you want to find out what angle is required for this thing to just start to slide, you'd find the inverse tangent to the coefficient of friction. You could use this exact same setup, this exact same relationship, to measure a coefficient of friction, static friction, between two surfaces. Something that you could totally find here. Dimensionless, 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 dimensionless. And it turns out that it doesn't depend on the mass. Interesting. We could also do other things with this inclined plane problem. What else could we do with it? Let's say the length of this ramp is some length d. And we're going to start with the block at the top, and we're going to allow it to slide down the ramp. We have some forces that are working on this mass. As before, we've got this normal force. As before, we've got the weight and the relative components. We've got this frictional force, mu times the normal force. This is now kinetic because we're going to allow the block to slide. So it's different than what we had before, but we get the exact same equations that we saw before. In the normal direction, we still have n minus mg cosine theta is equal to 0. But now parallel to the surface, I have mg sine theta minus mu n is going to be equal to m times a. The acceleration is going to be down the plane. The acceleration is down the plane in the direction of this component of the force. And as before, we can find out that the normal force is mg cosine of theta. I can plug this normal force in over here into this expression to see that mg sine theta minus mu, in this case k, mg cosine theta is equal to mass times acceleration. So looking at this, we have m in each of these expressions. We have m in each of these expressions. In fact, the acceleration is going to be sine theta minus mu k cosine theta times g. You may remember from the case where there was no friction, where the acceleration down this inclined plane was g sine theta. Now it's not g sine theta. Now it's an acceleration that's slower because of friction. Slower because of friction. This thing here in the brackets is dimensionless. Sine of some angle doesn't have units. Cosine of some angle doesn't have units. Coefficient of friction, dimensionless constant. So nothing in here has any units. The units of acceleration are the units of g. G is an acceleration, at least in terms of units. So here we could actually work through problems like this. And let's say the thing that we were trying to solve in this problem was how long does it take the block to get to the bottom of the ramp. So that's one thing that we could look for. We could see how fast is it going at the bottom of the ramp. And from this, those are kinematics problems. I think there's something on my paper. It's writing a little bit weird. So we have these kinematic equations. And for this equation, or for this question, how long does it take the block to get to the bottom of the ramp? If it starts at rest, if we call this position 0, we could use kinematic equation number 3 and find out, okay, well the acceleration is going to be 2d over t squared. Set that acceleration up here, and we could solve and figure out what the time is going to be. If we wanted to find out how fast it is going at the bottom of the ramp, then we might use kinematic equation number 4 to get that expression. So because here we know that it's going to slide a distance d, it's going to have some acceleration to v squared. Okay, so once we find out what the acceleration is, we plug that in, lo and behold, we could find out what's going on in a problem like this. So this is a pretty standard way of looking at friction in a problem. Friction is going to minimize the acceleration of our problem, but from there it's just kinematics. Once we know what the acceleration is, the problem is done. So before I end this video, there's one more example that I would like to look at, just to give a sense of how to put these things together. This is a problem in the notes here. Let's say we're to look at the problem shown here. In this problem, we have 2 different masses. One of them we know, M1 we know, M2 we do not know. One of these masses is sitting on some inclined plane. We know what the angle of inclination is because it's given to us. There's a coefficient of friction between M1 and the ramp. And we would like M2 to fall some certain distance in some certain amount of time. Because this is a free body diagram, what we're doing is finding accelerations, right? So we're going to have a uniform acceleration of M2 falling some certain distance in a certain amount of time with uniform acceleration. That's what this problem is really all about. Okay. So schematically putting it together, he calls this alpha, that's fine. This is M1. This is M2. We have one rope that's connecting these two things, as shown here. Now I'd like to look at some of the forces that are at play in each of these scenarios. We are told that M2 is going to fall. So acceleration and acceleration will be like this. Mass 1 has a normal force because it's sitting on some surface. M1 has some weight because it has mass. There is a tension pulling on it because it's connected to a string. We're told that there is friction. So these are some forces that are at play on mass 1. What forces do we have over here on mass 2? Well, this is also connected to the same string. So this T and this T are related to each other. This links the two free body diagrams. But M2 also has mass, so this is M2G. These are the forces that will create these accelerations. Okay, so now given this, what kind of equations come out of this? And we'll do the equations for mass 1 first. Maybe we can do perpendicular to the plane. Here we see that N minus M1G cosine of alpha is equal to 0. That's perpendicular to the plane forces. But we also see that T minus m1g sine alpha minus mu times the normal force, this is going to be equal to m1 times the acceleration. It is accelerating up the plane, so T is positive. This weight component is negative. This frictional component is negative. But the mass in the free body diagram is m1. Over here for m2, we only have one equation that comes out. m2g minus t is equal to m2a. This acceleration is down, so m2g and acceleration are in the same direction, t is in the opposite direction, and in both of these equations we don't know the acceleration and we don't know the tension. So what we can do is solve one of these equations for the tension and plug it into the other equation so that we can solve for acceleration. So here we see that the tension is m2g minus m2a. I can take this tension and plug it in over here, where m2g minus m2a minus m1g sine of alpha minus mu times the normal force, mu m1g cosine alpha. So what we've done is taken this and plug into this equation as well. This has to be equal to m1a. So here's where we included the t from the second equation. Here's where we included the normal force from this first equation. This puts everything together. And in this equation, there's only two places where we have the acceleration, m2a, m1a. So let's group those things together. I just pulled this over to the other side, leaving everything here on this side untouched. So we will have an m2g. We will have a minus m1g sine alpha. We'll have a minus mu m1g cosine of alpha. Okay, we could actually see that there's a g in each of these terms. So this is really m2 minus m1 sine alpha plus mu cosine of alpha times g. So there's a g in all of them. There's an m2 for the first one, m1 for the second one. I pulled the minus sign out. That's what makes this a plus, so that the acceleration is as shown here. Now the thing is, so this is not the most elegant. What we're actually looking for is mass m2, right? So eventually we're going to have to solve something to get m2s out of this. m2. There's an m2 here, there's an m2 here. But one thing that we are told is essentially what we need for the acceleration. Again, going back to our kinematic equations, we're told that it's going to descend a certain distance in a certain time. So the acceleration will have to be 2d over t squared. 2d over t squared. And so from here, it's really just algebra to figure out what m2 is, because I know what d in the problem is. It's given to me. it's going to fall some distance 12 meters. The time is 3 seconds. G is 9.8. M1 we know. The angle is given to us. The coefficient of friction is given to us. So now it's just a matter of solving this. Giving myself just a bit more time here. What I could say, M2 G minus M1 G sine alpha plus mu cosine alpha is equal to 2d over t squared times M1 plus M2. Okay, so what I need to do is solve for M2, right? And these are our equations. So I've got an M2 over here, I've got an M2 over here. We should try to get those two things together, right? So let's do M2 G minus 2D over T squared is going to be equal to 2D M1 over T squared plus M1G sine of alpha plus mu cosine of alpha. We can actually get a common denominator here. GT squared minus 2D over T squared. I could do the same thing over here. 2D plus G T squared sine alpha plus mu cosine alpha over T squared, which makes those disappear. M2 will be 2D plus GT squared sine of alpha mu cosine of alpha over GT squared minus 2D. Whew. Meters, this is, I feel like I'm missing something here. The units aren't going to be right. What am I missing? Oh, there's an M1 over here and an M1. So this gives me the units I need. Whew. Okay. Now we can plug in some numbers if we wish and see if we get something that's reasonable. Now from the text of our problem, we're told that M1 is 20 kilograms. We're told that alpha is 53.1 degrees. We're told that the coefficient of friction is 0.4. We're told that D, the distance it falls, is 12 meters. And we're told that the time it takes to do that is 3 seconds. So from here, we can pull out our calculator. Okay, let's do this argument here first. 0.4 times the cosine of 53.1 is equal to this. This is added to the sine of 53.1 is equal to this times t squared, which is 9, times g, 9.8, is equal to this, plus 2 times 12 is equal to this. This whole numerator is multiplied by m1, so times 20 is equal to this. Now you have to divide by this thing down here. (9.8) times 9 minus 2 times d, which is 12, which is equal to 36. That's how much M2 needs to be in order for that block to fall faster. Now, what would happen if we didn't have any friction, for example? So now this would be some smaller number multiplied here in the numerator with a bunch of pluses and stuff. M2 would naturally become smaller. I could get that acceleration with a smaller mass if I had a smaller friction. If I was to go to some higher angle, sure, sine of the angle would go up. The cosine of that angle would go down as alpha gets bigger. But it's probably going to be a net positive because coefficients of friction aren't terribly huge. So going to a higher angle is going to do some weird effects for what is needed for M2. We might have a lower normal force, which is naturally going to lower frictions and stuff like that. So there's lots of interacting parts that go along here. But what I wanted to illustrate was the fact that, we can create pretty complicated free body diagrams. We can create pretty complicated pretty complicated free body diagrams. We have pretty complicated scenarios, multiple objects interacting with each other. We have forces all over the place. We have systems of equations all over the place that we need to solve for all kinds of different unknowns. But you can do all of this stuff algebraically, move things around so that you know things that you know and you know things that you don't know, and things should work relatively quickly. But this is the process of going through a free body diagram problem with friction as opposed to one without. Now, if you are following along in Canvas, and you should be, there are a lot of examples beyond the ones that I show here for how to work with friction in free body diagrams. There is one problem in particular that I pulled from a different textbook from the one that we're using. It's from Surway and Jewett, where we have 3 different blocks. One of the blocks in the middle is sitting on some rough tabletop, but the other 2 blocks are just connected to it with strings, 2 different strings, so T1 and T2, great. And we have a bunch of different masses here, and we'd like to find out, well, what's the difference in this scenario if there's friction and if there's no friction? What if we were to guess wrong on the direction of friction? What happens and what do we have to do differently? It is a rather long problem, but it really highlights that difference of how we have to handle things differently if we start getting unexpected minus signs. So I do encourage you to go and look at the large number of additional examples that are in the Canvas shell. If you know how to handle free body diagrams, this is another one of those guaranteed topics for an exams. So if you're keeping track at home, there have now been 2 guarantees for problems on exam 1. One of them was projectile motion. You have to know how to do it. I guarantee it will be one of the problems on exam 1. Another one, free body diagrams. You have to know how to do free body diagrams, with or without friction. You have to know how to do them. This is another guaranteed problem. Now, on exam 1, there are 3 partial credit problems, right? You know 2 of them now. You are going to have to do projectile motion. You are going to have to do free body diagrams. So just be prepared. Now there is still one more part to this lecture. There's going to be a part D to this as well. We're going to look at what happens if we're dealing with accelerating systems, non-inertial reference frames, from some of the terminology from earlier. There's lots of scenarios where there's some acceleration in the problem that's a little bit unusual. And what does that mean for free body diagrams? It's how we look at circular motion in a slightly different way, related to what we saw in lecture 2.